Hellen will speak about a flexible organic solar cell based on a doped graphene anode. So when you're ready, please.
So can you see the screen?
Yes, that's working perfectly.
Okay. All right, so my name is Helen, come from the University of Queensland. Today I'm going to talk about flexible organic solar cell, which use graphene as transparent electrode. This work is a collaborative project with Chinese IMR, and also we got support from ANFF, ACAP, and RIA. And talk will be separated into 4 parts. And the first will be brief introduction. And then I will just introduce 2 types of graphene we use in this project. And then the third part will be we use these 2 types of graphene to fabricate organic solar cells, and then conclusion. So as we know, currently organic solar cells we use indium oxide as transparent electrode. But why we want to just replace it, or we want to develop other kind of transparent electrode, just because ITO, it has some issues like Roughness and also diffusion, and also some supply problem, especially when we talk about upscaling or flexibility. ITO gives some problem. So at this property, graphene, it provides good mechanical flexibility and a good chemical stability. And this is give it quite good property as alternative ones. I can't find my mouse, I'm sorry. So the normal route to fabricate graphene is chemical vapor deposition, is CVD. And then first we'll use CVD deposit on copper foil, and then transfer to flexible substrate we want to use. But this procedure only give one layer of graphene. If we want multiple layers, we need to repeat this procedure to get multiple layers. And Raman spectra will be one good way to check the quality of graphene. And let's look at this Raman spectra, this G and 2D intensity. If it is S2, that means there's a good quality of graphene, and this is for 1 layer graphene. And for graphene, there is one issue about sheet resistance. And this one effective way to reduce sheet resistance will be doping. And normal way would be top doping. These are kind of different ways to have been developed to just dope on top of graphene film after transfer. In this talk, we're going to use one is bottom top doping. This one is fabricate during this etching. So that means we use this BI into etching solution, and then copper and BI will combine to form complex, and then to get a kind of bottom doping. And in the following slides, I'm going to compare these 2. One is pristine graphene. The other one is doped graphene. It's just bottom BI doped graphene. So first, we want to see if it is has been successfully doped. So on left side, this one is pristine. graphene. Let me see. Oh, yeah. So this pristine film, and then from XPS, we can see this new bond already formed, and also this dopant also change contact angle, and it's just get a higher degree of here. So that's mean dopant is there, and it is successful doping here. And from these 8 photos, we compare pristine film and doped graphene film on PET. And visually, we can't see big difference. They are quite similar. And when layers number increase from 1 layer to layer 3 layer and 4 layers, we can see that transmittance will drop down. But from spectra, we can clearly see doped graphene film shows slightly lower transmittance. Yeah, and then let's move on to roughness. And this is AFM. Pristine film, when the layers increase for both type of graphene, we can see the wrinkles and roughness increase. But compare these 2 types, this BI doped graphene show less wrinkles and roughness. And this figure on left show this, we can see the BI doped graphene gives a bit less roughness. In the beginning, we talk about sheet resistance of this graphene. So why we want to give multiple layers of graphene, because when the layers increase, the sheet resistance will drop down quite sharply. And this is blue one is pristine graphene, and BI dope is red one. We can see the numbers the layer increase, the sheet resistance drop down. But for transparent electrode, there's always a trade-off between sheet resistance and transparent transmittance. So how many layers will be best one? From our previous work, which already found 3 layers will be the best, but let's see in this work. Then let's look at devices. For graphene device, we need to give this photoactive layer thickness pretty high. Normally it needs to be around 300 nanometer, more than 250 nanometer. And this one we use donor as PPD-T2, FBT, and PC70 BMS acceptor. And because this composite can give thickness 280 to 300 nanometer. And this is device structure on the left. We can see on top of graphene, we use molybdenum oxide. Actually, this molybdenum oxide is 30 nanometer. Is not normal for ITO device. Is normally for ITO, we use molybdenum oxide only 10 nanometer, but we have to use for graphene as 30 nanometer, because in our previous work, we published in this paper, and so we already found this molybdenum oxide very important, and the 30 nanometer is the best thickness, and it can decrease sheet resistance, conform the roughness, level the contact angle for different substrate, and also improve work function. If you want to know more details, you can just read this our already published paper. And now let's compare these 2 types of graphene when they're used into this organic solar cells. So this is IV curve. Top one is pristine graphene we use, and bottom is BI. Dark current, from dark current, we can see when these 3 layers gives the very low leakage for both type of graphene. And also we found 3 layers for both type of graphene is the best as well here. And also the leakage current for 4 layers will be the biggest one. This is because of roughness. We already showed in AFM that roughness is pretty high for 4 nanometer for 4 layers of this graphene. And also on right side is EQE. We compare them, and this EQE show also correspond to our JSC 2 layer and the 3 layer give the best JSC and also highest EQE. And now let's look at the table for this summary. So here we can see 3 layers for pristine graphene is the best. And the 3 layers Bi doped graphene also is the best in this doped. And ITO, this is on glass. So graphene on PET, and this is ITO is rigid glass substrate. So quite promising result. Let's see. Bi doped graphene, the highest efficiency already comparable with ITO substrate, ITO devices. So 96% of efficiency. That's and that is actually we can look at on the right figure. Our work show this result. This result already in the world, we can what position we are here. So from left side, we can see this Bi doped graphene for each layer. If each number of graphene will give a bit higher efficiency than this pristine graphene. And we published this work in this paper, so you can get more information from this this paper. And also for flexible devices, we need to know the mechanical flexibility. And these 4 figures, we compared this current, VOC, fill factor, and efficiency after 300 bending cycles. And compare these 2 types of graphene, we can see this after doping, it can keep this performance a bit better than pristine graphene. And then we upscale this device from 2.2 centimeters square to 1.6 centimeters square. And let's look at the efficiency. The efficiency dropped down quite some there. And then the major drop come from GSC and the fill factor. This is because, as we said, the sheet resistance is the problem of graphene steel. We need to work on this part more. And then this one is the stability. We put this graphene device under one sun for 15 hours. And we can see the stability is dropped down quite very quick. And within 5 hours is already 50% loss. So it looks the stability for graphene, this flexible device, although efficiency is comparable with ITO, but we still need to work on this stability issue. And then conclusion, would you use graphene-based anode to fabricate flexible organic solar cells, and the 3 layers give us the best result. And this doped graphene give us comparable result with rigid ITO cell. And yeah, but still have issues. One is when upscaling, we found this field factor dropped quite a lot, JSC dropped quite a lot. It's due to sheet resistance. And the other issue is stability. So we need to keep work on these 2 problems. Okay, so this is all my talk. Thank you.
Thank you very much, Helen. Very interesting presentation. I would like to open up if there are any questions from the audience, please.
Yes, please.
Yes, go ahead.
Yeah, thanks so much for this interesting presentation. I just have a couple of questions regarding the first one regarding the adhesion force between your substrate with the spin-coated graphene. And is there any way to increase this adhesion between the substrate and the graphene? The second question is regarding the thickness of molybdenum oxide. You mentioned that the thickness or the optimum one was found to be 30 nanometer, isn't it? So I use the molybdenum oxide for inverted structure solar cell, and I found that ultra thin, like 1 or 2 nanometer thickness is the best. And you know, I guess that the high thickness can give insulating properties. So what do you think of this for the other structure, if you can help me with this? Thank you very much.
Okay, yes, for inverted, you said 1 or 2 nanometer moly oxide is the best. Well, that's how to say, because from almost all published paper, the best thickness should be around 5 to 10 nanometer for even inverted or traditional structure. And why we use for graphene is 30 nanometer. One reason is the roughness. Actually, when we compare this graphene and ITO, yes, for ITO device, we use 10 or less 10 nanometer will be give the best one. But graphene, no, 10 nanometer is just not work. It will give leakage. So we have to use 30 nanometer. That's one reason. And the other one is 30 nanometer moly oxide is not insulated. It's not insulated yet. So although it will drop performance of ITO device a little bit, but it's not quite big. So yeah.
Thanks for that. And regarding the adhesion?
Okay, say again, do you have another question?
Yes, please. Regarding the adhesion with the substrate, between the graphene and substrate.
Sorry, can you say again?
I mean, what about the adhesion of your graphene with the substrate? Was it compared to ITO or not?
Oh, well, it's not. It can't compare with ITO because it can be easily scratched. ITO, you can scratch a little bit and you can't see any, but graphene, no, you can't.
So is there any way to avoid the scratching and open circuit effect during the fabrication process?
What I did is just put graphene on glass substrate and process it. But it's not so easily to be scratched. So although you may touch it, the surface, it won't affect too much.
Okay, thank you.
We have time if anyone has any other questions.
Yes, I do have a question regarding the thickness of the active layer.
Yeah.
How would the stability and efficiency be affected, or how different will it be if the thickness of the active layer is reduced? And secondly, regarding the N and K values of the active layer, how has doping using graphene affected the N and K values?
Okay, let's talk about the first one. The first one about photoactive layer thickness. And for this PPD T2 FBT PC70BM itself, it won't affect so much on thickness. So from 100 nanometer to 300 nanometer, the fill factor basically same, and GAC might increase from 100 to 300 now because it get more absorption. So for graphene, we don't use 100 nanometer just because we need to conform the whole graphene roughness and to get the device work. And for ITO device itself, 300 nanometer still the best one just because this donor and acceptor composite is the best at 300 nanometer. Is that what you want to know?
Yes, I was just thinking that as reported in some other papers, that when the thickness is high, the chances of recombination losses are also higher. So was thinking if reducing the active layer could be of any benefit in this case. But since you, from what I get, it's more like it's material specific. So yes. I think I'm okay. Yeah. Yeah.
Okay, and the other one is about optical constants. You said N and K, right?
Yeah.
Okay. Well, we haven't checked when we dope graphene and N and K of photoactive layer. So from my previous experience for optical constant, as long as there's no diffusion from contact from our electrode to photoactive layer, N and K shouldn't change.